Hello children, we are now going to continue with the same chapter, that is real numbers, standard 10th. Now we are moving to the next topic, that is fundamental theorem of arithmetic, and we will be studying about its application also. Children, the theorem which we are going to study now is known as fundamental theorem of arithmetic. Let me read out the statement initially, then I'll be explaining it in parts. Every composite number can be expressed or factorized as a product of primes, and this factorization is unique, apart from the order in which the prime factors occur. Children, the very first part of the question tells us about prime numbers and composite numbers. We all know that prime numbers are the numbers which have their factors as the number itself or the number 1. That is, 3 can be written as 3 into 1. And as far as the composite numbers are concerned, they can be written as product of factors of certain prime numbers. Let me take an example. 4 can be written as 2 into 2. So 4 is a composite number. So the statement goes as every composite number can be expressed or factorized as a product of primes. And this factorization is unique. Children, 4 can be written as 2 into 2. There is no other number which can be represented or written as 2 into 2. That is why the statement goes as the factorization is unique, apart from the order in which the prime factors occur. Now children, let me take another example, that is 20. The prime factorization of 20 is 2 into 2 into 5. Now children, this 2 into 5 can be written as 2 into 5 into 2, or it can be written as 5 into 2 into 2. The order may be changed. That is possible because multiplication is associative. So the order is not important, but there is no other number which can be represented as 2 into 2 into 5 other than 20. That is why the statement of fundamental theorem of arithmetic is every composite number can be expressed or factorized as a product of primes, and this factorization is unique, apart from the order in which the prime factors occur. There is a note given over here which is very important, and we have its use. Moreover, we are going to prove this statement also. For any two positive integers a and b, HCF of AB and LCM of AB is equal to a multiplied by b. That means the HCF of the given two numbers and the LCM taken as a product will give you the product of the numbers. We are going to prove it in the questions to come. Let us begin with exercise 1.2. Question number 1. Express each number as a product of its prime. So now this is already known to you. Still one example is solved. The very first sub question 140, it is 2 into 2 into 5 into 7. So 2 into 2 is written as 2 square, that you know. This is how you have to try solving the other 4 sub questions also. Next, question number 2. Find the LCM and HCF of the following pair of integers and verify that LCM into HCF equal to product of the two numbers. The first sub question is done for you. 26 and 91 are the given examples. 26 can be factorized as 2 into 13, whereas 91 can be written as 7 multiplied by 13. Children, in this case the HCF will be 13 because it is common in both, and LCM will be 2 into 7 into 13, which gives you 182. Now with this knowledge, we are going to prove the statement, mathematical statement. As we have to verify the statement, we have taken the left hand side separately and right hand side separately. The LHS, that is the left hand side, is equal to LCM multiplied by HCF, which are found to be 13 and 182. The product gives you 2366. Now the RHS, which is the product of the two numbers, the numbers were 26 and 91, so their product gives you 2366. Children, you can understand that these two numbers are same, and hence we have proved that LCM multiplied by HCF is equal to product of the two numbers. Now, question number 3. This is quite easy. Question number 3 is find the LCM and HCF of the following integers by applying the prime factorization method. Again, first is done for you. The rest too you can try yourself. The first example is 12, 15 and 21. You can see the prime factorization. 12 is 2 into 2 into 3. 15 is 3 into 5. 21 is 3 into 7. That is why the HCF, that is the common factor, it is 3. Whereas the LCM comes out to be 420. This is how you are going to try the other two also. Now we will be moving towards the next question, that is question number 4. Now question number 4 is flashed on your screen. It is given that HCF of 306 and 657 equal to 9. Find LCM of 306 and 657. So children, here the HCF is given to be 9 and we know that the numbers are 306 and 657. We are going to use the mathematical statement that we have just proved. That's why it is written that LCM into HCF equal to product of the two numbers. We have substituted the known values. So LCM is written as it is, whereas HCF is 9, and the product of the two numbers, it is written as 306 multiplied by 657. The rest is all mathematical. You get the LCM to be equal to 22338. Now, question number 5. Check whether 6 raised to power n can end with the digit 0 for any natural number n. Now children, if any number ends with the digit 0, it is compulsory that its prime factorization will always have 5 in it. Let me take an example. 10 is a number that has the last digit as 0 and its prime factorization is 2 into 5. Take any other number, say I take 30. So 30 can be written as 3 into 2 into 5. Again you have the number 5 as one of its factor. Here in our question, we are supposed to check for 6 raised to power 9, 6 raised to power n. 6 raised to power n can be written as 6 multiplied to it n number of times. That means we are focusing on finding out the factors for 6. The factors for 6, it is 2 into 3. And if it is 6 raised to power n, this 2 into 3 is actually written n number of times. Now children, according to the fundamental theorem of arithmetic, the prime factorization is unique. That is why, as you don't have 5 in the prime factorization of 6, this prime factorization will never end in 0. So the last statement reads as 6 raised to power n cannot end with the digit 0 for any natural number n. Let us move to the next question, that is question number 6. Actually, there are 2 sub-questions here. One is again solved for you, the other one you can try yourself. Explain why 7 into 11 into 13 plus 13 and the other one are composite numbers. We have to explain why it is composite number. Now children, 7 into 11 into 13 plus 13 can be understood as sum of 2 numbers. That means it has 2 parts. 7 into 11 into 13 is the first term, first part, and we are adding it to 13. So in the next statement, 13 is taken common. So the statement reads as 13 bracket starts 7 into 11 plus 1 bracket complete. Now if you solve that bracket part, you will get a number that is other than 1. And 13 remains as it is. So it is next written as 13 into some number. We are not interested in the other number. We know that it is not equal to 1. It is other than 1. So we can easily say that this number is a composite number because composite numbers are multiples of 2 or more prime numbers. Here, according to the fundamental theorem of arithmetic, every composite number can be expressed as product of primes. And this factorization is unique. This is the statement of fundamental theorem of arithmetic. And this is why we can say that the given number is a composite number. In the second example, you will see that there is the number 5 that can be taken common and you can proceed with similar steps. Now let's move to the last question of this exercise. There is a circular path around a sports field. Sonia takes 18 minutes to drive one round of the field and Ravi takes 12 minutes for the same. Suppose they both start at the same point and at the same time and go in the same direction. After how many minutes will they meet again at the starting point? Now here there are 2 people who are driving around a circular path. They are starting at the same point at the same time, moving in the same direction. The only thing that is different here is the time taken by each of them to take a round. Sonia is taking more time, whereas Ravi is finishing faster. Now children, if we start guessing our answer, after how many minutes they will meet. So if we think when they'll meet, that meeting time will never be lesser than these 2 numbers. Because Sonia is taking more time, it will be at least after few rounds that they will be meeting. That means it is not equal to 18 minutes also, and it cannot be any time that is less than this 18 minutes. So in short, we can say that the number which we will get as a solution when they will meet, that time will be More. It will be a number that is more than both 12 as well as 18. And it has to be a multiple of those two numbers. Then only they will be common and they will meet. That is why we are going to find out the LCM, that is lowest common multiple of 18 and 12, because that answer will be a multiple, or we can say it will be a common multiple, but it has to be the lowest common multiple because that is the first time they will meet. You all know to solve this question, as it's already told that you have to find the LCM of 18 and 12. You can try solving it and you will get the answer. Thank you for now.